Welcome back, everybody. Homework 2 is due. If you're racing to print it out or something like that, a few of you have already asked, just slide it under my door if I'm not there. That's okay. Homework 3 is out. I'll go over that on Wednesday in some detail, but have a look at it. Maybe get started with some things. There's a few implementation details on that. I'm going to have to teach you what Gibbs sampling is. There's a likely extension to that homework, but I have given you 2 weeks. So get started on it, but we have a number of things we need to cover. I need to teach you what Gibbs sampling is first. That's going to come after this lecture on credibility versus confidence. This will take a lecture or two. Friday, no in-person class. I'll probably start Gibbs sampling to some degree there. I will post a lecture. I'll probably have it posted for you on Thursday. I have to go out of town on Friday. So there is a class, but it'll only be a recorded edition. Sorry about that. Any questions? Peter,
Where are you going?
Alabama. So it might be a pleasure thing. So there's a vintage motorcycle event there that I'd like to go to. So I haven't been able to go for a couple of years because of everything, so I wouldn't miss it. Thank you. Thanks for asking. Okay. Credibility versus confidence. I need to tell you a little bit about this. At the end of last lecture, I started telling you what a credible interval was, or Bayesian belief interval. So I'll just point out real quickly, this is the thing that Bayesians talk about, Bayesian intervals. And what they are is, if you have some posterior distribution, so this is going to be the posterior. Usually we write something like this, pi theta given our data. How do we find that? Likelihood times prior. So this is going to be a function of theta. I'm drawing it in continuous space. In a credible interval, a 95% credible interval gets 95% of the area. And the interval is demarked by these bounds. So I'll call that the lower bound, and I'll call that the upper bound. You can do all kinds of things. There's all kinds of flexibility with this. Same is true for non-Bayesian intervals. So the non-Bayesians use the word confidence. And I suppose a Bayesian could do this too, but they have to have the right property. So these are what I would call frequentist intervals. And anytime I invoke the word frequentist, I do not mean non-Bayesian. So that's, a lot of people use the term like that. They'll use it to mean not a Bayesian. And that's just sloppy. So that's not what that term means. This means that there's some frequentist property. So it's guaranteeing something about if I repeated the thing over and over and over again. So that's the repeated process. And something is, you're conceptualizing something in this repeated process. Maybe as you repeat over and over again, something happens. In this case, it means if you construct your intervals over and over and over again, that the relative frequency should cover the true parameter 95% of the time, if it were a 95% interval. So these are coverage intervals. I kind of like saying it this way because it tells you what the frequentist property is. So that means if there's a true parameter, I'm going to call it theta. So this is confidence. I'll draw the same picture you would see in a Stat 101 class. Interpretation. So if I had some true parameter, I'm just thinking it's some value. It's right there. It's some fixed value. If I went out into the world and I collected data, I could maybe create an upper and a lower bound. So I'm just going to say you're going to collect data. and I'm going to compute some lower and upper bound. And I'm going to call that the interval. Okay, so imagine there's just a line right there. Just going to imagine this arbitrary thing just denoting where theta is. In this case, the way that I've drawn it is the lower and the upper bound consume theta. They cover theta. So this interval has theta inside, but we're not thinking about theta as the thing that's moving. We're thinking about the lower and the upper bound, or the things that are random here. And so the idea is that if I go out and I collect another data set, so if I repeated this process, I could compute another lower and upper bound. I'll give you an example in a moment. This one covers theta as well. Periodically, when I collect data, I won't cover. So I'll just say maybe this is the jth time I've done this. This is the jth time. And this interval does not cover. So these two cover. And this one doesn't cover. So these are the things that are random. So every time I go out, maybe I go out and I collect 100 data points from some process, I have some mechanism for computing the lower and the upper bound, and I see if it covers the truth. There's nothing special about this being an interval. It could be a disconnected region, so it could be a set of some sort, and part of your set has to cover. So I'm just drawing it as all very connected for just convenience. So the idea is, so I'll say for a 95% interval, just to give us some context, the idea is that if I go out into the world and I repeat this process over and over and over again, in reality, you'll probably just do it once though, is that your interval will cover whatever the rate is that you specify right here. So the idea is for a 95% interval is if we repeat it, everything. "95% of our intervals will cover." The truth. So there's been a lot of questions as what does this mean about actual theta itself? And people often like to mix their understandings between these two different types of intervals. Remember, in a Bayesian context, theta is the random variable. So it's the thing that we're imagining is, at least we're putting the randomness there on the thing that we don't understand. We're not saying it's random in nature. We're simply letting that random variable describe our uncertainty in that value. These intervals can be very different, or sets, and I'll show you an example of the set in just a couple minutes. Sometimes these are the same intervals, and sometimes they can be entirely different. So it's kind of nice. If you're a frequentist, if I kept coming up with intervals and I knew what true theta was, I could see how often I cover. And if I'm saying that my intervals are 95%, and in reality my intervals cover it 95% of the time, I feel pretty good about that. I kind of like that. On the other hand, the Bayesian is saying where they believe theta is. And that's kind of nice. So it's easy to understand. I think theta is in here on some probability scale. A probability scale is a measuring stick between 0 and 1. 1 means you highly believe it, 0 means you don't really believe it. And so I kind of like that. If you're able to repeat the process over and over and over again, and you're coming up with Bayesian intervals, and you're saying they're 95%, but they don't cover nearly 95%. Say, hey, I believe theta's in here 95% of the time. I have a method for coming up with that. And then you go and you check, and it only covers 30% of the time. You might not be happy with that. And so I tend to think in cases where you can repeat the process, you might want to calibrate your Bayesian intervals in a frequentist sense so that they do cover. And so in that sense, you can have both properties simultaneously. And we've seen that on the homework. So I had you construct intervals for P in the binomial experiment. And the Bayesian's intervals were covering better than the frequentist intervals, at least near the endpoints. At least in the way that we came up with those intervals. Those intervals, the classical ones, the frequentist ones, weren't really frequentist near the endpoints. So x bar plus or minus 1.96 times the standard error wasn't covering very well near the endpoints. So what most people mean is they'll mean asymptotic frequentist, that if n goes off to infinity, the intervals will have the property that they'll cover right. I hate that. It really drives me crazy to even think that way. Because if I had an infinite amount of data, my intervals should collapse to a point anyway. Standard error should go down to 0, and I would know what the truth is. So if I had an infinite amount of data, I don't need to do stats. So really, I mean, I guess I could, but everything just kind of works, and I get the truth. So it's not practically good enough for me just to say something is asymptotically frequentist. I want to know how well it works in different settings, and I want to describe that. So when somebody comes in and says, oh, I'm not a Bayesian, I'm a frequentist, here's my intervals, I usually ask them, did you check the coverage rate in like some sort of simulated experiment? And if they say no, I usually don't think they're actually a frequentist. I think they're just using words. And we see that a lot out in the world. So I don't want that to be you guys, and I want you to ask people if they say they're a frequentist, did you calibrate? Is it actually? What does n have to be? What parameter ranges do we have that property? So sometimes this is a wish and a prayer. Sometimes this is too. And so we need to kind of like sort this out through a few examples and understand what's going on. Again, what do I like? I like doing things as a Bayesian for two main reasons. One, the likelihood has all the information about the connection between the data and the parameters. Usually I can model build and kind of muck around with that, look at some diagnostics, and eventually say, hey, this is the likelihood I have for my data. I'm going to use this to describe the process. And then I have that prior that kind of regularizes things, takes care of me around boundaries of spaces. I can maybe inject information. I usually don't do that. Usually I don't have strong subjective information that I'm putting into the prior, but I can wiggle some knobs and get some properties out of my posterior. It always gives me this operating procedure. But if I'm repeating the process, I want my thing to have some sort of frequentist property. So frequentists, be delighted. I also like frequentist stats. I just do it through a Bayesian lens. Let's look at an example. This is probably the most confusing example out there, and it's the one where everybody starts. And poor students don't know what the difference between these two different intervals are. So I'm going to give you an example where everything works out the same. The Bayesian and the non-Bayesian will give you the same answer. So example. Everyone agrees. And what I should say about this, in terms of agreement, we're giving this, the frequentist and the Bayesian are going to give the same, report the same intervals, but their interpretation is different. So here's my example. X's are normally distributed, so I don't even have to do anything asymptotic. I'm going to say that I know sigma, make everything easy. Everything would work out just right if we did no sigma 2. We'd switch everything to t intervals versus normal intervals. I have n IID data points, so this is an IID process. I guess we can keep cutting that down. And I want to construct an interval. And so what usually, this is what a classicist will do. So where I should say maybe some sort of a frequentist. So what they're going to do is they're going to construct a statistic. They're going to look at something like this. Construct a stat. Usually it's not any old stat, and there's a lot of theory behind why you might come up with certain test statistics. I'll say a little bit about it. In inference class, we say a lot more about this. But I might say x bar minus mu over sigma squared over n, and I'm going to square root that thing. Okay, so this is your typical sort of estimator. This is your standard error. For this test statistic right here. So it's the variance of x bar. And this is true mu right here. I don't think I said a lot about this in our inference class that we did last year. I kind of took some of the time out of that. But this is what's called a pivotal quantity. And it means I can work out the probability of this thing, and it doesn't have anything to do with that parameter mu that we don't know anything about. And so this test statistic doesn't have anything to do with mu, but I've written mu down. So what I actually mean is that the distribution of this doesn't have anything to do with mu. So this is just a rough understanding of where some of this theory comes from. Does anybody know how this is distributed? I know 95% of you do. I hope I'm calibrated at least. That's at least a lower bound. What's distribution does this follow? Normal, very good. Which one?
0, 1.
0, 1, thank you. Yeah, it's almost too painful to say it, thank you for it. So normal 0, 1, it doesn't depend on mu. So this is normally distributed. The variance is decreasing and we're scaling the variance. We're subtracting off the mean, whereas x bar, centered at mu, it has variance sigma squared over n. So if I divide that out, I divide out this mu. And all of us have done that before. So this is normal 0, 1. So what the frequentist will continue with is I'll write down a probability statement on this. They'll say z is between some bounds, lower and upper. The question is what's random in all of this? And the only thing that's random is x bar. That's the random thing. They're not Bayesians. They didn't place a prior. They didn't upgrade mu to a random variable. They didn't condition on x bar. They're going to describe how much this statistic kind of warbles around, how much it moves. So what they mean by that is if you go back out into the population and you repeated this over and over again, x bar is going to be a different number every time you do this. It's going to flood. And so Bayesians like to think about that as well, but we utilize that in a different way. So this is random. And possibly I can set this equal to some number, 0.95. Maybe I want to figure out what the lower and the upper bound is so that this is 95%. We write this thing down. We've got some z, it's centered at 0. It has variance 1. And I can figure out what this lower and upper bound is. So that this mass in here is 95%. And possibly I want the shortest interval, and you can convince yourself that if you wanted the shortest interval, these tails are going to have to be symmetric because the normal distribution is symmetric. So they should be symmetric around 0, these bounds. So this is going to be 2.5%. This will be 2.5% of everything. And most of us know what these numbers are. And so there's only one choice for them. This will be minus 1.96, and this will be 1.96. So these are my critical thresholds. Hopefully my Stat 101 teacher is impressed that I can remember all of this and say it in just the right way. So Here's what they end up doing with this. Is they replace this with its definition. This is going to be x bar minus mu over sigma over root n. And they're going to do something called pivoting. So basically, they're going to shuffle everything around in the inequality. You guys have probably seen this before. So that's the. So let's just write it down in 2 steps. X bar minus mu over sigma over root n. Write it the way everybody else writes it. Less than minus 1.96. 1.96. And this is my 95% statement. I used the 95% to come up with these thresholds. And I'm going to just pivot around mu. And I'll let you work through this. Be a couple minus sign flips that you'll need to play around with. But this is going to look like this. This is going to be x bar minus 1.96 times sigma over root n, the standard area. And this will be x bar plus 1.96 sigma over root n, the standard area. So shuffling this around and just having mu in the middle, again, I'm going to have to distribute that negative sign, and it's going to flip the bounds around. I'll let you work through all of that. But these are equivalent statements. Question is what's random in this statement? What's random now? Can you say it again? Very good. I can't fool Siri. So, you know, I was hoping somebody would say, I guess mu is. No, wrong. This is the thing that you get, your Stat 101 teacher gets upset with you about. And it's like, well, why'd you stick it in the middle of everything? It looks like the probability statement is about this. Now, these are the random things. This is random. Bless you. That's the lower bound. And the upper bound. This is also random. That's my upper bound right here. So if we were doing the analysis, I'm kind of imagining that I'm going out and I'm collecting data. I'm computing x bar. I know sigma in this case. So I just plug it in, and I'm computing all these lower and upper bounds. And this would have the property that these intervals would cover 95% of the time. And there's nothing wrong with that. That works out perfectly. So, and in fact, this isn't even an asymptotic statement. For any n, this will work. So even if you just have n is equal to 1, and you can try this out at home, and 95% of the time on average, this will cover. That's not a statement about big N. This is an exact interval, and everything works out great. And everybody likes this interval. The Bayesian's going to go about things a little bit differently. So the Bayesian's going to construct belief intervals. So credible intervals. And I will just kind of point out, credibility and you say confidence there, they're just words. Like, nobody ever said what they meant. They're not descriptive of anything whatsoever. And so if you go back in time to the 1920s and you start talking about confidence, people didn't know what it was. And they wouldn't argue about it. And nowadays, we just push it down your throats and say that's what it is. Everybody accepts this, moving on. But this is not a statement about mu itself. And the question is how is this? This is describing uncertainty in the process. It's not an inference about mu per se. And so what I would say is the interpretation is, if you ended up going about this, you go out to 100 scientists, you do calculations for them, you give them intervals, 95% of those scientists have been served correctly. They've gotten intervals that cover the true parameter. And 5% of the time I give scientists wrong intervals. They don't overlap. So if I'm following the frequentist paradigm It's really a statement about me as the statistician, how good you are. It has nothing to do with the individual inference itself. That's kind of funny. Jack Good, that we've talked about in some detail, that was a member of this department for a long time, and at least in my opinion, the guy that coined the name Bayes. I always give him the credit, but I give it to all three of those guys, Dave Finetti, Jack Good, and Savage. I'd say Jack Good was the catalyst for making that a thing, and Savage ended up doing it. He said, frequentist intervals are designed in such a way that it protects the statistician's posterior. Ha ha ha. So it's a joke. And he wrote this in some paper some time ago, and I don't think I can dig that up in 10 seconds, but you guys can go and Google query that. So it's just some quick wit, I would say. The Bayesian is going to base everything off of the posterior. So again, they're going to get the posterior. In our example, let's just go back to this exact same example. We've got our likelihood function. So same example that we're studying. Our likelihood function on mu. We've got all of our data, sigma in here. And I'm going to write this down the easy way. You could write it down in product form. This is going to be e to the minus 1/2, I'll write it down like this, mu minus x bar over sigma squared over n. And if you wanted to write down the normalizing constant, you could do that. So, but all the action is right here. This is proportional to, I goes from 1 to n, 1 over root 2 pi, sigma e to the minus 1/2 xi minus mu squared over sigma squared over n. Same things. So if you never know how to build your likelihood or whatever, just do it in the product form. Always come in through a product and then you can simplify it later. If you know things about sufficient statistics, you can jump straight to that. X bar is sufficient for mu. Nothing else gives me information about mu, so long as everything's normally distributed, other than x bar. So I can just build a sampling distribution for x bar and then think about it as a function of mu once I plug in x bar. So I build my likelihood. The second part to this is to come up with a prior. So I'll ask you guys, which prior? What would you pick? Say that somebody walks in and they're playing around with data just like this. They don't tell you anything important about mu. They don't tell you what they think it is. They just say, all I have is data. And I really don't know. So in that context, which prior would you pick here? Yeah, probably. Which one? What is it? It's proportional to a constant. Yeah, so we usually write something like this down. And you should have all kinds of reasons to pick that. But I'll give you more as the class continues. We'll be doing Jeffrey's priors after Gibbs sampling. That's what comes next. If you can't wait, there's a lecture up there if you just go back to about that timeline in last year's classes. So flat prior on here seems to work good. Lots of reasons to come up with that prior. So the posterior looks like this. So for our example, my mu given x, I'll write down that I know sigma squared is going to be equal to, it's going to be at least proportional to this thing, e to the minus 1/2 x bar mu minus x bar squared over sigma squared over n, and I'll multiply by the prior. That's my prior right here, and I recognize this thing instantly. I don't have to look at the quadratic term or the -2 linear term and expand, because it's in another form that I recognize. So this is the probably most canonical form that people play around with, the normal distribution. So you recognize this thing is centered at x bar, and has variance sigma squared over n. So this is a normal x bar, and variance sigma squared over n. So then I'm going to do the exact same thing. I'll play around with my posterior distribution, and I might ask, where's a 95% belief interval? If you wanted the shortest one, it's going to be symmetric. I'll say a few things about that in a moment. And I could figure out where these control limits are to have 95%. This thing is centered at x bar, it still has variance. You can work through the calculation. This is going to be x bar plus 1.96 sigma over root n. And this will be x bar minus 1.96 sigma over root n. And so the Bayesian's credible interval. So the Bayesian interval is going to be this thing. X bar minus 1.96 sigma over root n, and all the way up to x bar plus 1.96 sigma over root n. And I give you the exact same answer that the person working through pivotal quantity will give you. But the interpretation is different because the Bayesian is thinking mu is the random thing. So this is mu on this axis. And this right here is pi mu given x and sigma squared. I'll just leave it out. So they hand you the same interval, and they have two different interpretations. I'm going to just add, this interval covers exactly. How do I know that up front? You wouldn't. You'd need to check. But I could maybe go back to my classical training and say, it's the same interval, and it's an exact interval, so I have all kinds of reasons to already know this thing covers. If you don't know that, you just check to see if it covered, but it does. I think that's great. So no problems with me. I'll take this one, even though it's the exact same thing as that one. The reason I'll take this one is because I can say it covers. I can also tell you it's the shortest one, and I could convince you of that. And it's a belief interval. So it's also where I believe mu exists. So I get everything for that, just by being a Bayesian and saying, I multiply by 1. Now, not everything is just as nice as this. So, but here's a case where everybody agrees, and that's probably why we shouldn't start out with normal examples, because everything's kind of idealistic in that case, and everybody does agree in these sort of examples. I'll show you an example in a moment where everybody does not agree. Yes, please.
So for the credible interval, it's centered at x bar, but for the confidence interval, it's centered at 0. So
Well, I ended up pivoting. So if I standardized everything, I would have the exact same thing.
okay.
So these are the same in disguise. So we worked with, I threw z into everything. So this was z, which was x bar minus mu over sigma over root n. So this was a standardized distribution. If I unstandardized everything, I'd be working with the exact same distribution. So they're kind of the same in disguise. I'll let you think about that a little bit. It really is the same analysis that's going on. Okay, so everybody agrees here, but that doesn't always happen. You can kind of see when people would always agree. So if the likelihood function is symmetric in the data as a parameter that you're doing inference on, and you use a flat prior, the Bayesian and the non-Bayesian are going to agree on quite a lot of things. So if there is that symmetry between those two distributions. And so it's not a coincidence, it's just the way it is. But in a lot of problems, the data and the parameter are not symmetric, and we wouldn't see an alignment like this. Let me just tell you a little bit about HPDs, just real quickly. And then I'll show you an example where the frequentist and the Bayesian disagree with each other. And I'll argue maybe the Bayesian is giving you a little bit more, and maybe that's every frequentist would probably do something like that, but the question is do they have a paradigm for it? Okay, so HPDs. These are highest posterior density intervals. This is just a coincide lecture, take 2 minutes. These are the Bayesian shortest intervals because they're highest density. And so to have all of the mass in the highest density region, it means that I'm looking at the shortest region. Those are equivalent to each other. Let's just look at an example where everything's not quite so obvious. So imagine I had something like this, some interval right here. This is going to represent some posterior distribution. This is a function of theta. You probably wouldn't want to get the equitail interval in a case like this. So the equitail interval might chop off 2.5%. So I'll say this is the equitail or equal tail. So this might be 95% in here. But this answer isn't very good for obvious reasons, because it's not really distinguishing what's happening over in this mode versus this mode. And I kind of like this stuff because it has high density compared to that. So this would be a case where you want these denser intervals. So this is probably not great. So this L and this U are probably not great. It's convenient, it's easy to do. I've seen worse atrocities. But I wouldn't feel great about using that equitail thing here. If it were slightly skewed, I might do it, just because sometimes it just saves time and how much are you going to get out of this other calculation. If you want the HPDs, and there's a lot of software that's built into R. I've written my own versions of this for my examples. Usually they're based off of some approximation where you're discretizing something continuous and adding mass just by adding up little discrete units of mass. So if I have my interval, it's maybe like this. Make that a little lower. Here's the idea. To construct one. Pretty much all your algorithms are going to work like this on a discrete scale. They're just going to discretize everything. In high dimensional space, this can be a little bit of a challenge just because you need to discretize things a lot in high D. But basically, I'm going to start with a bar. And it's going to run through the top of this. So I'm just going to lower this down. And it's going to hit the top of all of this. And at this point, I haven't added any mass up in this distribution. I'm going to slightly drop this thing a little bit, maybe right there, and I can add up mass that falls into the distribution. I can just add that up, all that mass, and say this thing is like maybe 48%. So if I'm looking for a 95% interval, I haven't added all the mass yet. So what I'm going to keep doing is I'm going to slowly drop this bar. You'll notice what I'm doing is I'm grabbing the high density stuff first. And this will give me the shortest interval by doing this. So I add a little bit more mass in here, add that up. If it's not 95%, I keep going. And I keep going until I've added up 95% of the mass. Let's say this does it right here. So I add that together. I take that point right here, that point, and I add all this mass together. And say at the end of the day, all of this stuff is 95%. So I would have this right here, this, and this. Would define my region. So I'll just say this is L1, U1, this is L2, U2. That's just what I'll come up with right now. So these are for my Bayesian things. So L1, U1, union L2, U2 is a 95% HPD. So they're not always intervals. Sometimes you get sets, disconnected intervals. And that would make sense. And it would probably be worth going through some computation of taking your likelihood, your posterior function and trying to find this. There's packages that will do this with samples. So if you handed a bunch of samples from your posterior, it will form a continuous approximation based off of those samples, probably using something like density estimator. So if you've ever played around with those, this can be pretty nasty in high D, and when I say in high D, I mean like 5 dimensions. So, but they might do something like that, create that approximation, and then figure this out for you. So conceptually, it's an easy thing to think about, but you can see in high D that there is a computational curve. And packages will help you do that. If you do see things with 2 modes in it, you should describe that modality. It's probably super interesting, and you should stop and talk about it for a long time. Like, what does this mean? This is really weird. This is interesting. And the longer you talk about it, if you can write about it for a long time, you'll become a professional academic, and they'll give you a job. So, okay. So that's at least what an HPD is. Let me give you this example where everybody disagrees with each other. There's a paper online that I posted for you this morning, and it's called Jeffries, Fisher, and Neyman. I might have the order messed up. Could they have agreed? So paper online says Fisher, Jeffries, Neyman, in some order. Could they have agreed? So who we're talking about is Neyman from the Neyman-Pearson lemma. If you know about him, you have Ronald Fisher, the old geneticist, feisty geneticist, and Jeffries that we'll be talking about a little bit later, who's a quote-unquote objective Bayesian. Pretty good naming. Who doesn't want to be objective? But I'll point out later, he's a bit subjective. It's just, again, a word. The answer to the question that the paper asked, could they have agreed? No. Fisher never would have agreed with Neyman on anything. It doesn't matter. You know, the sky is blue. No, it's not. You know? So they would not have agreed. And it kind of shows this debate through this example. So if you want to read through that paper, read the first couple pages of it, and it'll kind of tell you the different sides to everything. There's also a rejoinder that you can find. So there's a commentary section where everybody came in and said to the author of the paper, Jim Berger, we have a different opinion. And so you see the squabbling begin. There's an old faculty member, emeritus faculty member here, Deborah Mayo. She's one of the people that comments on everything and tells Jim he's wrong. Jim responds back and says, no, you're wrong. And if you ever see these two people at a conference together, that will be the whole conversation. So they'll just go back and forth, no, you're wrong, you're wrong, you're wrong, you're wrong. So you'll have to make your own decisions here. Here's the example. So let's say you're given data. This is a pretty easy problem. Xi's are going to come from a distribution. I'm going to say you either get to see this value theta plus 1, or you're going to get to see the value theta minus 1. So I'll say xi is equal to this, and this happens with probability 1/2. And this also happens with probability 1/2. So there's 2 outcomes. They're just as likely as each other. I'll make this problem a little bit harder, and I'm going to say I can go from 1 to 2 And this is very important, the 2. Okay, so this is one of these examples that's just set up to make you think about things. What happens in these simple cases, and how do the different paradigms react to a problem like this. I'm going to show you real quickly a 75% confidence interval. And I'll let you leave thinking about why this is the confidence interval. And the next time we'll do the Bayesian thing and see what the Bayesian says the answer is. But a 75% confidence and this will be a set. This is not an interval. So nothing special about intervals. In the context of this problem, it kind of makes sense that you might not want a continuous interval. This is the unknown thing. So it's just a Bernoulli coin flip, but in this case, we're telling you the probabilities, and we're not telling you where it's centered. So theta is acting as a shift right, effectively. It's just shifting these things around. So 75% confidence set. Usually the notation for this is going to be a function of the data. That's the random thing. So we're thinking about the frequentist answer. And this is obviously set up to make the frequentist look not great. And I'm not saying that any card-carrying frequentist would give this as an answer. But this is a 75% confidence set. So this is going to be if x1 is equal to x2. So there's going to be cases here. I'm going to report back x1. Oh, let's say they're not equal to each other. I'll give you x1 plus x2 divided by 2. So I'll just give you those two things. Let's imagine that this is theta plus 1. This one's going to be theta minus 1 because they're not equal to each other. So maybe I see these numbers and it's a 3 and a 5, for example. If I average them together, I get back 4. Okay, so this thing would be 4. This is going to give me the correct answer. This is always correct, right here. And arbitrarily, I'm just going to say if x1 is equal to x2, so I didn't get to see any variability, I'm going to just report back x1 minus 1. This is an arbitrary choice. I could have given you back x1 plus 1. Okay, I want to just point out to you in this is correct 100% of the time. So let's imagine theta was, just to give us some bearing, let's say theta was 4. So I ended up reporting back this thing as a 5, and this thing right here was a 3. Right here. If I average 5 and 3, 8 divided by 2 gives me back 4. And I get back the right answer. So if x1 is not x2, this is right. This is right, however, 50% of the time. Okay, so if theta was 4, and I ended up giving you back this thing right here. So sorry, hold on. Let's say theta was 4, and I ended up seeing a 5 right here. 5 minus 1 is 4, I gave you back the right answer. However, if this was a 3, because they're equal to each other, then 3 minus 1 is 2, and I gave you the wrong answer. Question is how often does this happen? This happens 50% of the time. And this happens right here 50% of the time. You can think about that is, I'm going to give you one of these two values. On the first draw, what's the probability that I match that value? It's 0.5. So, because these each happen with probability 1/2. So let's just do the math. I'll give you back the correct answer 100% of the time. If this is true and this happens 50% of the time. So 1/2 times 100% or plus. This is correct 50% of the time, and it happens 50% of the time. %. No problem with the math. Everything is mathematically correct. Here's the problem with this answer, is you're going to hand whatever this is back to somebody and you're going to say 75%. That's what you're supposed to do. How confident are you? So if I ended up seeing this right here, you'd say, well, it's a 75% confidence set. It's a statement about the process. If I did this over and over and over again and I scored how right I was, on average, I'd be right 75% of the time. So the big mess up is that you always report 75%. So if I ended up seeing this, I would report this as an answer and they'd say, how confident are you? 75% confident. That's a terrible answer. And if you ended up seeing that right there, you'd say 75%. And that's all messed up. So that's the problem with confidence on its own, is it's really not a statement about a parameter. You shouldn't be reporting this, and I'm not saying anybody would. There's a discussion in that paper where they say there's something called the conditional frequent history, where you condition on an ancillary statistic that's distribution that doesn't depend on the parameter, and you can fix this up. And the correct sufficient statistic is basically the difference between these two values, x1 and x2. If it's a 2, you should report something else. If it's a 0, you should report a different answer. And they walk you through that discussion. And if you want to read through it, that's fine. It won't be part of the class, but it's something you can do. The trouble is nobody has a real operating paradigm for using that in general. Which ancillary statistic do you condition? So confidence on its own is not a very appealing answer. You know, you don't want to just say something about the process. You want it to be conditional on what you've actually seen on that draw. We'll come back next time and we'll develop the likelihood for this model, so be thinking about what that is. We'll be discussing which prior we should use, and then we'll see which answer the Bayesian gives back. So just be thinking about all that. Thanks, you guys. That's it for now. I'm going to have to give you some time back one of these days. It's always this like